So I was asked to talk about the formation, evolution, heating, enrichment of the ICM, including the AGN in dense environments. So I think this is a pretty big topic for 20 minutes. I think it's a pretty big topic for a conference, but I'm going to do my best. A number of these topics have come up in one way or another throughout the week. So I'll try to be brief in those cases. I'll try and give a brief overview of the topics, focus maybe on key tools and methodologies, broad progress since 2017, and also what progress we might make soon with new facilities and with improved methods. So even though it's day 5, because we are such a broad audience, I still want to spend 1 minute on what the ICM is and how we measure it. So the ICM, the intra-cluster medium, refers to diffuse hot gas, which permeates the space between galaxies in a galaxy cluster. What sort of temperatures and densities are we talking about? We're talking about 10 to the 7 to 10 to the 8 Kelvin. We're talking about densities 10 to the -4, 10 to the -2 per centimeter cubed. So how do we probe the ICM? Typically, we probe in 2 key ways, which are going to come up time and again in this talk. So first, we collect X-ray photons that the hot gas radiates. It does this via thermal Bremsstrahlung emission. The emission is proportional to the gas density squared, so it gives a strong signal in the center of clusters. So that's going to be one take-home message. There's also the Sonia-Zeldovich effect. So here a CMB photon is upscattered by the hot electrons in the intercluster medium. The result is essentially a transfer of photons from like the low to the high frequencies, and this is going to leave a decrement of photons at the low frequencies. And this is what you're seeing illustrated here in this gap that you're seeing in the ALMA HST image of RxJ1347. Now, an important take home for this method is that the CMB radiation energy density increases with redshift in a way that cancels out the dimming of cosmology. So the SC effect basically is roughly independent of redshift, and that the take home there is it's great for finding high redshift clusters. So on to the topics I was asked to discuss, starting at the beginning with the formation of the ICM. The first takeaway message is going to be that the ICM is continually forming. So when we're probing how the ICM forms, we have kind of 2 key techniques, I suppose. We can look back in time and try and identify the nascent ICM. And we can also look to the outskirts of clusters and try and identify how the ICM is forming as gas and galaxies. They're going to get funneled along these filaments. They're going to go through accretion shocks. Gas gets stripped and perhaps joins the ICM. So there are excellent simulations of this. I'm going to highlight quickly. Elke Rodiger has some nice simulation papers showing survival time of the gas and how the length of these sorts of features that you see depend on plasma physics such as conduction, viscosity, configuration of the magnetic field, and how instabilities grow as the gas is stripped. And you're seeing also a beautiful image, observational image of this process occurring in this optical X-ray image by Dominic Eckert and collaborators. We see a group falling into Abel 2142 and being progressively stripped as it does so. So on to the first technique, the birth of the ICM. This isn't something we've yet observed. We're reliant on simulations. One such simulation is from Renahan et al., which I'm going to play for you here. What you're seeing being simulated is the temperature of the gas, 10 to the 5 to 10 to the 7 Kelvin, as many galaxies are collapsing and forming a brightest cluster galaxy. Now, we've seen this simulation mentioned earlier in the week, in fact, on Monday, in the talks about SBT2349 at a redshift of 4. So these simulations and others suggest that the first collapse, and in this first collapse and this intense period of star formation results in supernovae feedback, which already begins to enrich and build the ICM. I mentioned we don't have a lot of observational evidence for the birth of the ICM yet, but we have identified remarkably mature galaxy clusters around a redshift of 2, with sometimes smooth, relaxed X-ray gas, and indeed lots of it. So there are a few examples here: JKCS041 at a redshift of 1.8, SBT0459 I'm showing here at a redshift of 1.7, and XLSSC122 which was selected from the XMM large-scale structure survey at a redshift of 2. And we've heard about a couple of these clusters at least already so far this week. So we know mature relaxed ICM can be in place by a redshift of 2, but we also see evidence for incredibly rich and bound protocluster structures. So what I'm showing here in the figure is the velocity versus radius relation for members of the SPT 2349 protocluster structure. And this is from Riley Hill's nice paper in 2020. And this particular target has been talked about also in a couple of talks on Monday from Riley and from Scott Chapman. And this sort of target is a wonderful target for identifying a nascent ICM, the sorts of things that we just saw in Doug Renahan's simulation before. So what progress should we expect to make on the question of when the ICM forms? So I think we're in a good position to make a lot of progress. This is a recent compilation of galaxy clusters so far identified through SC techniques. But what you can see is that we're building sizable numbers of virialized structures above a redshift of 1 already. And this is only going to get better. So next generation X-ray observatories, for instance, eROSITA may not be brilliant at high redshift, but it's going to be fantastic pushing towards lower masses and towards the outskirts of clusters. Athena will be fantastic for pushing towards these higher redshift clusters around a redshift of 3 or so. Unfortunately, with Athena, it will suffer confusion, not just with point sources within the cluster, but also foreground and background sources. Links, however, will be spectacular if we get links, and that should allow us to be able to distinguish point sources and diffuse gas even in nascent ICM. So I think that's incredibly exciting. It's not all X-ray telescopes. We have CMB stage 4, which is simply going to be an incredible cluster finder. And there's also clusters going to be identified from LSST and from LSST combined with other infrared telescopes as well, which will push us both down the mass range and to high redshifts. So that's from the cluster side. But we're also making a lot of progress, as we've heard, from the protocluster side. So this time I've taken a figure from a white paper by Overseer and Kashikawa from 2019 and doctored it a little to try and add in the various surveys I've been listening to throughout the week. It's not an exhaustive list, I'm afraid. So do let me know if I've missed them. But I think this is already impressive. So we're already finding these objects. There's just a question of if we can detect the ICM in them. So detecting the ICM is one thing. How does it evolve over time? So thermodynamic properties of the gas encode information on processes that lead to the thermalization of this gas. As well as on non-gravitational processes, such as things like gas cooling, AGM feedback, there's shocks, there's turbulence, there's bulk motions, there's cosmic rays and magnetic fields. A common profile that people use is the specific entropy. So this is related to the temperature and the density to the -2/3. Why do people use it? It's favored because it tells you something about the structure of the gas. So in the presence of gravitational processes only, the low entropy gas will sink to the bottom of the potential well, the high entropy gas will float. You're left with a profile that predictably decreases towards the core, and it's going to scale self-similarly. So it's nice and predictable. However, heating, cooling, mixing, convection, all these sorts of processes are going to alter your entropy profile. So the entropy of the gas will increase when the gas is heated, lower when the gas is cooled. For instance, if you were heating the gas before it fell into a cluster, that could raise the entropy profile. Heat injection, perhaps from something like AGN at the center of a cluster, could raise the entropy profile. Gas cooling out of the cluster could raise the entropy profile. Turbulence and bulk motions will affect this. And there's also a phenomenon called clumping, which could decrease the measured entropy profile and has been observed to do so towards the outskirts of galaxy clusters. So you'll recall I mentioned that the X-ray gas is proportional to the density squared. So if there are small pockets of high density gas, so for instance, infalling substructures falling into your cluster, this will interfere with your total measurement of your entropy, and it will serve to decrease your entropy. And this is actually seen in the data. You can see on the left-hand side from this review by Walker et al. In 2019, where most of the entropy profile is relatively nice. As you get towards the outskirts, it looks very messy, possibly evidence of a turnover. However, once clumping is accounted for, these profiles tend to go back to the self-similar profile that's been recovered. So what about the actual evolution of this ICM? So with Redshift, do we see evolution? The short answer here, but I think we'll have some longer answers today, is no, not really. There are parts of the profile that where heating effects and clumping dominate scatter and things like this. But in the better behaved parts of the profile, so far the data is largely consistent with a self-similar expectation. So, however, on that front, I think we're going to do brilliantly in the coming years. Again, with more targets at high Z and at low mass. But another methodology for investigating ICM evolution, which I think is going to be more and more important, is the combination of X-ray and SC measurements. So X-ray cares about the density squared, the SC cares about the integrated pressure. So that one's going to be more sensitive towards the outskirts. The combination of the two data sets can span the full extent of the cluster. So combining these data sets together can be really powerful, not just for these sorts of profile measurements, also for understanding processes like AGM feedback in clusters and so on. And I think we're going to see really great improvements there. So that's ICM evolution and some of the tools we use to understand it. What processes affect this evolution? So here we're getting onto the heating, cooling, enrichment part. Everything that injects energy, facilitates cooling in the gas, is going to be affecting the ICM evolution. Now, some of these have been mentioned before. A lot of the heating and cooling processes have been mentioned before. So I'm not going to talk about those very much because of time. I'm going to focus instead really on enrichment of the gas and what progress we've made there and what progress could we make there. So the take home on the enrichment is going to be that the ICM is enriched. It's enriched over its full extent, and that measuring these abundance patterns can provide clues about the chemical enrichment history of the gas. So sadly, we haven't improved our knowledge quite as rapidly since the first GCF 2017 meeting as we'd hoped, and that's just because of the sad demise of the Hitomi satellite, which would really have been very influential in this field. However, in the brief time it was up there, it did get some excellent data, and you can see that excellent data on the left-hand side here. It also enabled detailed studies of chemical abundances. So for instance, what you're seeing on the right-hand side is a figure from Aurora Simonescu's paper in 2019 of the abundance measurements and a comparison to models of supernovae yields. And the take home from this, 5 minutes, thank you. The take home from this is that none of these models could actually recover all of the line ratios. So this could be due to systematics, that could be that enrichment varies perhaps in spatial regions in the cluster, and we need better spatial resolution as well. It could mean that we need better stellar nucleosynthesis models. So even without Hitomi, though, the field's been pushing forward. So I'm just going to highlight a few examples on this slide. So Francoise had a nice paper looking at systematic differences and abundance ratios recovered when using spectral models that rely on different atomic codes. So this is trying to understand the systematics in doing these sorts of measurements. There's Simone Ghazadi's paper here presenting a new methodology for improving accuracy of metallicity measurements. So here we're trying to also improve the current methodologies we have. And you can see also in that image that the metallicity appears with radius appears to flatten out. So this is something that's been seen in quite a number of studies, and the metallicity flattens the outskirts at a value of about 0.3 solar. There's a paper from Adam Mance that I'm showing here, where he's looked at metallicity measurements at a redshift of 1.7 in SPT cluster 0459. Those have a similar outskirts metallicity value. So here we're really seeing that the ICM must have been enriched early, and it's had little to no evolution in the bulk of the gas thereafter. Another method where we're pushing on is through simulations. And right on the bottom here, I'm showing here simulations of the radial profile of the gas and redshift evolution in metallicity from the C-eagle simulations. And I think we have now highlighted some discrepancies with the observations and the simulations. So there's a lot of work to be done here still to understand this fully. The observations need to become more precise. We need to understand our systematics, our selections, and perhaps the models need to have better physics of how the gas gets enriched and distributed. So while there's some way to go, we certainly have experiments coming along which are going to be immensely useful. So GRISM is the replacement for Hitomi, which will be with us in a few years. And also the XIFU on Athena is going to give us both that high spectral and spatial resolution that we wanted. So the gas is enriched, it's well mixed. What could be doing this? So chemical enrichment is going to be driven by star formation, but mixing and distributing gas is going to be a range of processes. So galactic winds, turbulence, and of course AGN outbursts. So this allows me to segue to my final topic, the including AGN part of the talk. So there are many varied results on the importance of AGN in dense environments. What they do there, if they're there at all, in greater numbers than the field. Why are the results so varied? So AGN are diverse, they are time varying, their hosts are diverse, and they're comparatively rare, which makes selections and also statistical arguments about them difficult. Part of their diversity is in accretion mode, and we typically talk about the accretion mode as being in two key states. So kinetic, mechanical mode, radio maintenance mode, and then the radiative quasar wind mode. But of course, we also see, thank you very much, we also see bright radio quasars. We shouldn't confuse these sources with, for instance, the inefficiently accreting radio sources we see at the centers of brightest cluster galaxies at low redshift. So there are many ways we can characterize AGN in dense environments. There's clustering and direct observation. I'm going to concentrate on direct observation and focus on the cluster environment. So there are some things that are fairly firm and some that need more investigation. Massive central galaxies in cool core clusters often host radio AGN. I think that's fairly firm. X-ray and optical AGN number densities tend to decrease with cluster radius in a qualitatively similar way to star formation. I think that at least on the qualitative level can be said quite firmly. There are mixed results on outskirts triggering, merger triggering, and for that I refer you to Matt O's review and also some of the talks as well that we've heard this week. On the evolution side, the story is not yet clear. So there's some evidence that as we go to higher redshift, we might be seeing triggering of AGN in clusters rather than suppression. We do need to be a little careful with these observations. So there's some caveats we need to worry about. The mass range varies with redshift that we're looking at. So we need to make sure in terms of mass of our clusters, we're comparing apples and oranges, but also the dynamical state of our cluster might matter. So when we're comparing clusters with protoclusters, we need to make sure really that we're still looking at apple and apple comparisons, not apples and ripening apples. My last take home from this before my summary slide is going to be that we do see a halo mass dependence of AGN number densities. This was tentative at first, but I think it's starting to get firmed up in the X-ray and optical AGN. And I refer you to a poster by Ben Floyd for he's beginning to look at the infrared AGN dependence on halo mass. And I think I'm out of time. So I will leave you with my summary. So the ICM is important for galaxy evolution. I hope no one needs convincing of that yet. The ICM is constantly forming. I think we're on the cusp really of detecting it, which would be really cool. X-ray and SE are complementary tools that are going to elucidate our high Z ICM processes. The ICM is enriched and the abundance pattern is going to be really informative, and we're going to learn a lot about that soon. And AGN in dense environments are diverse, but some do live in clusters and in protoclusters. And at least in the cluster side, there is a halo mass dependence that we're starting to see. I'll leave it there.